the service. Hello and welcome to the course on the transmission of data packets, Ethernet. In the course on data transmission theory, we already heard that all data transmission processes are governed by so-called protocols. A protocol is based on the rules for communication on a layer, that is, implementation of the service. It describes the format and meaning of the exchanged messages and packages. Each layer has its own protocols. Using the protocols, the sender is able to communicate with the receiver on the same layer. In this course, we also got to know the TCP/IP family of protocols, which provide the basic functions for transporting data packets on networks. In addition to the Ethernet protocol, which is not specified in the TCP/IP family, IP and TCP are among the basic protocols of network technology which we always need. One of the most important protocols of the TCP/IP protocol family, without whose contribution data transmission wouldn't be possible, is the ARP protocol, the Address Resolution Protocol. The purpose of the protocol is to resolve an IP address to get the MAC address we absolutely need for data exchange with Ethernet. In addition to this standard protocol, there are still several special protocols for Ethernet primarily concerned with redundancy on networks. In this section, we'll take a closer look at both protocol types, ARP and the redundancy protocols. Have fun! Let's begin with ARP, the Address Resolution Protocol. According to the RFC 826 standard, ARP is one of the most important protocols of the TCP/IP family of protocols. Here you can find the structure of an ARP packet. Click the image for more information. ARP is often assigned to layer 3. ARP is responsible for address resolution, however, which actually isn't a task of layer 3. As ARP and IP are closely linked, ARP would be correctly assigned between layers 3 and 2. A frame essentially consists of 3 subsections: a header, the payload, and the trailer. Depending on which Ethernet frame we look at in more detail, the individual composition of the header changes. As we already learned in the course on data transmission theory, network devices are addressed via their IP address on OSI layer 3. The data is sent one layer lower on OSI layer 2 with Ethernet on a local network, however. As well, Ethernet uses the MAC address of the respective subscriber for sending. We'll run through the process now. We'll return to our practical example where a computer is linked to a printer over a LAN cable. Both components are set up for networking and have an IP address. The two devices communicate with one another after being switched on for the first time, however. What's going on? First, we send the print order to the printer. First, the check determines whether both components are on the same network. Second, if this is the case, the computer and the printer are both on the same network, the ARP cache of the computer is checked to determine whether a MAC address for the known IP address of the printer is already saved. As we are carrying out this action for the first time, there is no information about it in our ARP cache. Third, with ARP, the computer places a request with the IP address of the printer on the network here, asking the owner of this IP address to please disclose its MAC address. As the receiver MAC address, the broadcast address, FFFF, is used in the Ethernet frame here, so all computers on the local network receive the ARP request. The destination MAC address within the ARP request is not filled out in order to indicate that the sender of the ARP request, that is, our computer, would like to find out this MAC address. 4. The stations, in this case there is only our printer, compare the sent IP address to their own. If they don't match, the request is rejected. If the printer notices that the IP address is referring to it, it sends an ARP response with its MAC address as a unicast directly to the computer. For this purpose, it extracts the fields with the MAC address and the IPv4 address from the ARP request and uses these values as its response. 5. The computer enters the information into its ARP cache. 6. The computer processes the ARP response of the printer, saves the MAC address as a destination address of the destination, and enters this information into its ARP cache. As the MAC addresses are now known to both components, they can exchange data with one another. In addition to the assignment of the IP address and MAC address, the entries in the ARP cache are comprised of specifications on the entry time, the period of validity or age of the entry, and, if applicable, the protocol type. The amount of time an entry remains in the ARP cache before it is deleted depends on the implementation and is usually a few minutes. As soon as an entry in the table is used, its process time is extended. The ARP cache prevents an ARP broadcast from being initiated to the same destination again and again for each data packet. Using our second practical example, several computers access a printer on the same network. All the devices are then managed with a single switch. In network technology, a switch or Ethernet switch is a device which physically and logically links network subscribers to one another. Switches have a certain intelligence and only forward telegrams to the desired addressee if known. The other network subscribers receive nothing from the data exchange. there's no physical connection between each end subscriber. With a unicast, a decision as to which telegram is forwarded to which ports is made using the MAC addresses. This means that a switch is a device which works on layer 2 of the OSI model. Multicasts and broadcasts are forwarded to several subscribers or all subscribers. Ideally, each end subscriber only receives the data intended for it in this way. In network technology, a switch or Ethernet switch is a device which physically and logically links network subscribers to one another. Switches have become the standard components for linking Ethernet subscribers to one another. Now let's take a look at the redundancy protocols. Redundancy prevents failure of data transmission at the individual points of a network. This means that redundancy is an effective means for improving the productivity and availability of a network. As shown in the diagram, communication between end devices is not negatively affected when a primary transmission route between two switches fails, because there's a secondary transmission route. If redundancy is not implemented, communication can no longer occur between two end devices if a failure occurs. High network availability can be achieved with reliable devices, redundancy, and error-tolerant systems. Using a network topology which enables fast convergence for isolating an error makes sense. Typical redundancy requirements include automatic reconfiguration after a line failure, automatic reconfiguration after port deactivation, automatic reconfiguration after a component failure, load distribution, and the monitoring of redundancy mechanisms. Redundant lines are therefore very helpful when it comes to achieving increased availability or being able to carry out diagnostics if an error occurs. To prevent the undesired circling of packets due to looping, Layer 2 redundancy protocols are required. What's this circling of packets all about? This problem occurs on Ethernet networks when sent broadcast frames are distributed within a broadcast domain. The reason for this is the basic way switches work by handling broadcast frames. Even though one and the same frame is transmitted, all ports are flooded by each switch in order to deliver the broadcast to each network subscriber. The only exception is the port at which the frame was received. In the scenario shown above, this means: Step 1. A broadcast frame sent from switch 1, above, reaches the two switches 2 and 3, below. Step 2. The frames are sent again from there, but are now only exchanged between switches 2 and 3. Step 3. The frames are sent back to switch 1. The process is repeated and generates several copies of the original data frame. Over time, the Ethernet connections are further filled up endlessly by this process unless at least one of the Ethernet plugs is disconnected, for example by pulling out the cable or switching off the port. In network technology, this problem is known as the switching loop on layer 2 or broadcast storm. The process is repeated and generates several copies of the original data frame. Over time, the Ethernet connections are further filled up endlessly by this process unless at least one of the Ethernet plugs is disconnected, for example by pulling out the cable or switching off the port. In network technology, this problem is known as the switching loop on layer 2 or broadcast storm. We have looked at the ARP protocol and important redundancy protocols. Now it's time for a brief summary. We wanted to know, why do we need the ARP protocol? We have learned the purpose of ARP is to find out the MAC address of a device on the network for the corresponding IPv4 address. We wanted to know, why do we need redundancy protocols? We have learned redundancy prevents failure of data transmission at the individual points of a network. This means that redundancy is an effective means for improving the productivity and availability of a network. We wanted to know what requirements are placed on redundancy. We have learned automatic reconfiguration following a line failure, automatic reconfiguration following port deactivation, automatic reconfiguration following a component failure, load distribution, monitoring of redundancy mechanisms. We wanted to know what important redundancy protocols are there. We have learned MRP, STP, RSTP, PRP, HSR.